My name is Drew Harper, and I'm an engineer with the California Lighting Technology Center, and I was the project manager for this project I want to talk about. Purpose of this presentation in this project was to evaluate the performance of distributed DC lighting systems. So as many of you know, most commercial buildings use AC or alternating current power distribution systems that receive electricity directly from the grid. Because of this, most subsystems in these buildings, including lighting, are designed to be powered directly off this AC infrastructure. However, most common LED lighting systems and most other digital electronics require DC power to operate. This necessitates an AC to DC conversion for every instance where DC power is needed. And in theory, with increasing DC load, the AC to DC conversion efficiency will improve, and therefore it could be more efficient to aggregate the AC to DC conversion and distribute DC power throughout a building. So again, the theory is that with increasing scale of AC to DC conversion, this could result in a higher AC to DC conversion efficiency. With this in mind, there are two general approaches to a distributed DC power system. The first would be to aggregate and centralize the AC to DC conversion, and this can happen at a variety of scales. A power supply could distribute DC power throughout a whole building. You could have centralized power supplies to power individual rooms of a building, or you could have centralized power supplies for each building subsystem. And the second method is to get the DC power directly from renewables like solar and wind. Although in practice, most of these renewable systems invert the power and feed it back to the grid, or they use an energy storage system rather than directly powering DC devices. So there are some advantages, potential advantages and disadvantages to a DC lighting system. Some of the advantages are, again, there's that higher theoretical AC to DC conversion efficiency. You can utilize existing building infrastructure. We'll talk about it in a minute, but the PoE system or power over Ethernet system can piggyback off of existing IT or information technology infrastructure. They can be safer and cheaper to install since they're classified as low voltage class 2 electrical systems per NEC. However, there are also some drawbacks to DC lighting systems. There can be an increase in electrical losses in the conductor since you're transmitting DC power instead of AC power. There's currently a higher upfront cost associated with these DC lighting systems compared to comparable AC systems. And there's also a lack of standardization between manufacturers in terms of cabling, connectors, and communication protocols. And also many of these DC lighting systems are pretty new, so they could be unfamiliar to the people who are actually installing them. All right, so we conducted a market assessment and identified 12 manufacturers that had commercially available DC offerings. These DC lighting systems, we then subdivided into two main categories: power over Ethernet or PoE, and low voltage DC, which we have referred to as LVDC. And we'll get into both of those in the next slide. We also spoke to lighting reps and electrical distributors to identify a widely used AC lighting system that could be our control or a baseline. So yes, some of the differences between these two categorizations that we came up with. As I mentioned earlier, PoE lighting systems can use, or they do use, information technology infrastructure such as power switches, CAT cables, routers, and IP communication. They also conform to Cisco's UPoE standard, and they operate below 60 volts DC and 60 watts DC per channel. They're capable of transmitting both power and data across the same CAT cable. And again, they're class 2 electrical systems per NEC. The LVDC systems are, they also operate below 60 volts DC, but there's no standardized cabling or communication protocol across manufacturers. And because of this, there's a wide range of possible power outputs per channel, and data and power can be transmitted on the same cable or separate cable. So PoE is a more specific version of LVDC, if you will. All right. So to specify our AC baseline system, again, we spoke with multiple electrical distributors and identified this 2x4 LED luminaire as a commonly used commercial AC luminaire. For the study, we procured 9 2x4 luminaires with a 4,000 lumen output at 35.5 watts or 116 lumens per watt, a correlated color temperature of 3,500 Kelvin with a 0 to 10 volt dimmable driver. the low voltage DC system, we purchased this 9-channel LED driver. It has 9 output channels with a maximum of 226 watts of DC power. It communicates via DMX protocol. And as a load to this power supply, we procured 9 2x2 LED luminaires with 2018 lumen output at 16 watts or 126 lumen per watts. They're capable of dimming down to 0.2% and have a maximum cable run between the power supply and the luminaire of 150 feet. 2 things to note at this point. When we specified each DC system, we wanted to maximize the load that we could put on the power supply. So we picked luminaires with the highest rated wattage that we could find. And secondly, in terms of system architecture, this LVDC system is the most basic of the DC systems that we looked at, and in that it's essentially one centralized driver for 9 luminaires, and that's pretty much it. Speaking of system architecture, before we get into the specifics of the PoE systems that we evaluated, it'd be good to talk about what a PoE system architecture looks like. So basically, a PoE architecture consists of 4 main components. First, you have a gateway computer that hosts the control software. It allows for programming and commissioning of the system, as well as it provides a user interface for the system. Then you have your PoE switch, which acts as a power supply for the system, but also handles communication between the node and the gateway. And then finally, you have your PoE node, which is basically a communication endpoint, and it provides DC to DC conversion and current regulation to the luminaire. And then finally, you have your luminaire, which is similar to a traditional luminaire, but it's driven by this PoE node instead of an LED driver. So the first of the 2 PoE systems we looked at, which we'll refer to as DC Manufacturer 2, we procured this 8-port power switch that has 480 watts of output power. It is also conforms to the Cisco UPoE standard, as all PoE systems do. And then as a load for the power switch, we procured 8 2x4 PoE-enabled luminaires that have 6,500 lumen output at 50 watts or 131 lumen per watt. And again, in order to load the power switch as much as possible, we bought the biggest luminaire, 50-watt luminaire that they offered. And then finally, there's the PoE node, which is attached to each luminaire. Again, it handles the communication from the power switch, and then it gives regulated current and voltage to the luminaire as needed. Oh, skip one. All right. Second PoE system we looked at, which we'll refer to as DC Manufacturer 3. Similar to the first, we use the exact same power switch. In fact, most PoE systems that we could find, the manufacturer suggested to use this power switch. So we use the same power switch, and then as a load on the power switch, we went with this. We bought 8 of these 40-watt white tunable LED luminaires. So these luminaires are, again, they're 40 watts. They're actually white tunable, and they have integrated sensors. And for this study, we weren't interested in color tuning or in the sensors. We just wanted the luminaire we could buy for the system that had the highest wattage. So this was the one. And then here it's important to point out 2 main differences between the 2 PoE systems that we looked at that actually did impact the findings. So one main difference is that the DC Manufacturer 2 system allows you to dim the luminaires through the user interface. So basically, you could sit at a screen and you could dim all the luminaires to whatever setting you wanted to. The DC Manufacturer 3 system does not allow you to do any dimming unless it sees a PoE-compatible dimmer switch on the network. So basically, the other system, you could have only luminaires connected and you can still dim it through a software interface. But for this system, if you don't have a dimmer switch connected, it will not allow you to dim. And we'll get into why that's important later. Another thing to note is that the DC Manufacturer 2 system, let's see if I can go back a slide. As you can see here, the PoE node has 2 RJ45 connectors. One is for power in, and then the other is to allow you to connect another PoE-enabled device in series. What that allows you to do is you can hook up all 8 luminaires to each of the 8 ports of the PoE switch. But if you wanted to hook up a sensor or a wall switch, you could daisy chain it off of one of these fixtures and not have it occupy one of the 8 ports. So where that factors in is that in our evaluation, we varied the load on the power switch in two different ways. And basically, when it came time to vary the load via dimming all the lights at once for the DC manufacturer 3 system, we had to plug in the dimmer switch directly into one of the 8 ports of the power switch, thereby not allowing us to fully load the power switch with 8 luminaires. We could only use 7 because it had to have a dimmer switch, and you're not allowed to daisy chain things or sensors or wall switches with the DC manufacturer 3 system. So hopefully in a bit, it'll become a little more clear how that impacted the findings. So for our laboratory evaluation, we use a California Instruments function generator as a highly stable AC power supply to provide power for the entire lighting system rather than plugging it into mains voltage. And to take electrical measurements, we use both a Zytron 2802 power analyzer and a Yokogawa power analyzer to measure current and voltage at various points throughout the system. So our lab setup consisted of these testing racks you can see on the right that house the 8 or 9 luminaires with enough space in between them to allow them to thermally stabilize. When taking measurements, we placed 1 luminaire on the benchtop and connected our meters as seen on the right, while the remaining 7 or 8 were on the rack. And then for each system, again, everything was powered by that California Instruments function generator, and we collected all of our data using those 2 power analyzers. So in order to characterize the performance of each system, we first identified every point of power loss within the system. Essentially, we took electrical measurements before and after every point where power is either consumed, transformed, rectified, etc. On the right, you can see a generalized diagram to exemplify this. And after we identified every point of power loss, we then varied the load on the power supply in 2 different ways to evaluate its performance under different operating conditions. So the 2 methods of varying load on the power supply were first, dimming all luminaires in set increments and taking measurements at each step. So for example, we set all 8 luminaires to 100% output, take measurements. Then we dim all luminaires to 90% and take measurements, and so on. And secondly, there's a method of sequentially removing 1 luminaire from the power supply while the remaining luminaires operate at 100% output. So for example, set all 8 luminaires to 100%, take measurement, unplug 1 luminaire from the power switch, set all 7 to 100%, take measurements, remove another one, and repeat. Both methods of varying load were intended to replicate the real world, help us understand what the optimal conditions were for this lighting, for each lighting system. So for example, is it more efficient to run all luminaires at 80% or to remove one of them or to turn 1 or 2 of them off? So we made 2 primary assumptions during our testing. First was that the luminaires that were sitting on the rack were performing exactly the same as the luminaire that was being probed. This assumption allowed us to only meter 1 luminaire at a time. The second was that the lighting systems were operating under what we considered to be the worst case scenario in terms of cabling. So for each lighting system, we used the maximum cable length and the smallest cable gauge recommended by the manufacturer. So for the PoE systems, this looked like 100 meters of 24 gauge Cat 5e cable. And for the LVDC system, this was 46 meters of 18 gauge stranded cable. And then before taking any measurements, we allowed all the luminaires to thermally stabilize per LM79. And finally, we devised the following performance metrics to evaluate each system. You have power supply efficiency, which was defined as the total DC power out of the power supply divided by the AC input power to the power supply. Then there's line loss, which was defined as the difference between the DC power at the node and the DC power at the output of the power supply. And there's the node efficiency, which is defined as the DC power out of the node divided by the DC power into the node. And then there's peripheral power consumption, which is defined as the AC power into all peripheral devices, such as gateways, routers, etc. And then there's total system efficiency, which is defined as the DC power at the luminaire divided by the total AC input power plus any peripheral power consumption. So for the baseline AC system, we only conducted the dimming test as there's no centralized power supply to remove luminaires from. So the sequential test didn't really make sense. The only source of power loss in the AC system was from the AC to DC conversion at the driver, and this system was able to achieve a maximum efficiency of 86%. Okay, the LVDC system achieved a maximum system efficiency of 79%. The graph on the right shows the system efficiency for each testing method. So as you can see, there's minimal difference in performance between the two for this system. Additionally, the line losses for this system and for all the DC systems matched the predicted line losses that we calculated using physics and the known resistance of the conductors. For the PoE systems, the power switches performed better when varying the load by removing fixtures rather than dimming. So on the graph on the right, you can see both DC manufacturer 2 and 3 performed slightly better when the power switch was when the power switch load was varied by removing luminaires as opposed to dimming all the luminaires. So the node efficiency for each system were determined during the dimming test to characterize the node performance across the full range of luminaire output. The DC manufacturer 2 system achieved a maximum node efficiency of 92% compared to 89% max node efficiency of the DC manufacturer 3 system. It should be noted that the DC manufacturer 3 system was unable to load the power switch as much as the DC manufacturer 2 system due to requiring the use of a dimmer switch in place of one of the 8 luminaires. So if you think about it, when I mentioned earlier, the theory is that if you load your AC to DC conversion as much as possible, so if your power switch is 480 watts, in theory, the conversion efficiency will be optimal the higher the load you put on it. So the DC manufacturer 2 system was able to load the power switch more than the DC manufacturer 3 system. So that could have contributed to why it achieved a higher efficiency. Then we have total system efficiency. So the DC manufacturer 2 system was able to achieve a maximum efficiency of 75% total system efficiency compared to 73% for the DC manufacturer 3 system. And this could partially be contributed to the greater node losses in the DC manufacturer 3 system. All right. Okay, overall, the baseline AC system achieved the highest maximum system efficiency of 86% under our testing conditions, and this was 7 to 13% better than each of the DC systems. For each system, the greatest source of power loss was that AC to DC conversion. Losses due to DC to DC conversion at the node also contributed significantly to the overall power losses, even with a node efficiency of upwards of 92%. Additionally, line losses were as significant, if not more significant, than node losses. And the peripheral losses, however, were less than 2% and would be even smaller for a larger capacity system, as you wouldn't need to have another gateway or another computer to run a 2000 watt system, for example. As I mentioned earlier, we tested these systems under what we considered to be the worst case scenario in terms of cable length. Realizing that it's unrealistic to have 8 luminaires that are 100 meters away from the power supply, we generated computer models to determine what real-world cable lengths might actually look like. To do this, we set the following constraints in the model. The number of luminaires is either 8 or 9, depending on the system. There was a target light level of 27 foot candles at 2.5 feet above the floor, a power density of between 0.23 and 0.3 watts per square foot, and 10-foot ceilings. We also assumed the power supply was located in the plenum directly above the center of the room. And then we let the software generate optimal lighting layouts from which we could calculate the distance from each luminaire to the center of the room and therefore get cable length.
Andrew, we have just like a 1 minute left.
Okay, I have just one more slide, I'm almost done.
Sounds great.
This table shows the results of the computer modeling, and as you can see, the real-world cable lengths were significantly shorter than the worst-case scenario. Using these new cable lengths, we could calculate new line losses and then new system efficiencies for each system. And as you would expect, each system did perform better with the more realistic cable lengths as the line losses were less. However, each DC system was 5 to 9% less efficient than the AC system, even with this factored in. So in conclusion, the AC baseline system is more efficient than the DC systems across their operating range. The DC systems introduce additional sources of power loss compared to the AC systems in peripheral losses, line losses, and losses for DC to DC conversion. The PoE system had more points of power loss than the LVDC system. And also our testing seemed to confirm or seem to agree with the fact that with higher loading on the power supply, you get a higher AC to DC conversion efficiency. And finally, the real world cable lengths would be significantly shorter than the worst case scenario. And finally, the next steps, the study only analyzed DC systems of upwards of 480 watts when there are systems that go up to 2000 watts. So an evaluation of these higher capacity systems could show that the increased AC to DC conversion efficiency is enough to offset the other sources of power loss, making it as, if not more efficient than a baseline AC system. However, there are also AC systems that advertise efficiencies upwards of 90 or over 90%. So those should also be considered too. And finally, an internet-enabled AC system, for example, would suffer efficiency penalties from peripheral devices such as a router, but it would make it more comparable in terms of control to the DC systems we evaluated. So we should look at AC systems that have better controls capabilities as well.